Have you ever just, looked at nature and wondered what puts the brakes on everything? Like, why doesn't one type of plant or one species just completely take over the whole planet? Well, it turns out the answer is usually hiding right there in plain sight. It's a rule that controls everything from a single cell all the way up to an entire ecosystem.
So, let's jump right in with a kind of weird question. What on earth could a single tiny bacterium possibly have in common with that viral video that everyone was sharing last week? The answer? It's all about the explosive power of exponential growth.
You see, exponential growth is all about momentum. It isn't just adding 1 plus 1. Nope, it's about multiplying. 1 becomes 2, 2 becomes 4, then 8, 16, 32, and you see where this is going. Before you know it, you get this massive explosion of numbers. It's literally how things can go from being tiny to totally huge, almost overnight.
All right, so let's actually look at what this growth explosion is like when there's absolutely nothing holding it back.
I mean, just try to wrap your head around this speed. A population of bacteria, if you give it the perfect conditions, can grow at a mind-blowing 300% per hour. That's not just doubling, folks. That's quadrupling every single 60 minutes. It's just pure, unchecked biological power.
But we both know this can't be the whole story, right? If this was actually possible, we'd be swimming in a planet-sized soup of bacteria. Something has to step in and hit the brakes.
And this right here, this is where our perfect little mathematical model crashes right into the messy, complicated, and beautiful reality of the real world.
And that collision gives us two very different stories about growth. On one side, you've got the fantasy, that perfect J-curve of exponential growth, which kind of pretends you have infinite food and space. But then on the other side, you have reality, the S-curve, which has to face a fundamental truth of all life. Resources are always finite.
And this dose of reality introduces a super important idea called carrying capacity. We often just call it K. Think of it like a maximum occupancy sign for an entire environment. It is the absolute limit, the ceiling for how many individuals a habitat can possibly support before things just start running out. So what are these resources that create that ceiling anyway? Well, it's a lot like baking a cake. To get life, you need a very specific recipe with a whole list of ingredients.
And you can see here it is a pretty complex recipe. You've got your main ingredients, the stuff you need tons of, like carbon and nitrogen. Then you've got secondary ones. And then there's this whole list of micronutrients that you only need the tiniest little pinch of. But here's the catch. Everything on this list has to be there at the right time for growth to actually happen.
And just like with any recipe, it doesn't matter one bit if you have mountains of flour and a truckload of sugar if you only have one egg. The ingredient you have the least of, that's the one that controls the whole show.
Okay, let's use this recipe idea for algae growing in a lake. You've got tons of carbon in the water, check. Plenty of nitrogen coming from the air, check. Sunlight is beaming down all day, check. But then you get to phosphorus and, whoops, the supply is tiny. It doesn't matter how much of everything else you have. Growth is going to slam to a halt right there.
Let that really sink in for a second. Growth doesn't just slow down when it hits that limit, it stops, dead in its tracks, all because the single most scarce ingredient is all used up.
And that one scarce ingredient, it has a special name. We call it the limiting nutrient. It's the one element that holds all the keys. It alone decides what the carrying capacity is for that entire ecosystem. It is the ultimate bottleneck.
So now that we get this weakest link idea, we can use it to solve a pretty common mystery. What is it that makes a lake suddenly explode with green life?
We know there's a limiting nutrient, right? Some kind of bottleneck controlling everything. So what is it? What's the one ingredient that's holding back the show in most of the world's freshwater lakes?
And the answer, in the vast majority of cases, is phosphorus. It's naturally really scarce, because unlike nitrogen, it doesn't just float around in the air. It has to be slowly released from the weathering of rocks. And yet, biologically, it is absolutely essential. It actually forms the backbone of our DNA and the energy currency of every single cell, a molecule called ATP.
So, let's put it all together real quick. On one side, you've got that fantasy J-shaped curve, a world of unlimited resources leading to infinite growth. And on the other, you have the reality of the S-shaped curve, where one single limiting nutrient creates a hard ceiling, that carrying capacity, K.
And here's the bottom line. That one element, phosphorus, is the master controller.
If you want to know how much algae, how many fish, how much life a lake can support, you just have to measure its phosphorus. It's really that direct.
And that leaves us with a fascinating and maybe a little unsettling final question. We've basically cracked the code. We know what the natural off switch for growth in a lake is. So, what happens when we humans come along and start adding more? What happens when we remove that unseen limit?